This is going to be lecture 9.1. And we're going to talk about boundary layer, introduction to boundary layer theory. What are we going to do with this boundary layer theory, and why is it useful? Why do we use it? What is all this fuss about the boundary layer theory, and why students actually don't remember it? Let's actually think about all those things and let's learn all those. Now, this is going to be an introduction first. Introduction to convective heat transfer. So we want to actually have an idea about convective heat transfer, and the boundary layers are the most important objects to study when you actually talk about the convective heat transfer. Okay, we're going to learn about concept of the boundary layer for momentum transfer. So you can ask, okay, professor, decide one thing. Are you going to do the heat transfer or momentum transfer? Which one are you going to talk? Well, actually, we need to study both simultaneously to have an idea about how the heat is being like convectively transferred. Imagine that you have a solid which has a surface temperature of Ts, and you have a fluid either flowing or stationary, and it has a temperature of Tf. And so far, we have said Qs, the surface flux, is equal to H times Ts minus Tf. And what was the name of the scientist who said that? Newton, right? Assuming that we know the value of H. Right? Which is associated with the convective heat transfer at an interface, right? So far, we have derived a lot of equations. We wrote down a lot of equations. Today we're gonna do the same thing, but I want to use more verbal like definitions, verbal arguments, because most of the things are done like starting from intuitive arguments and then going deep into the formulas. So I want to actually develop some intuition about the convective heat transfer first before actually getting our hands into like derivations and formulas and symbols and so on. Okay, so I'm going to write down a lot of things. So let us learn about how H can be estimated. And what is the mechanism? What the mechanism of convective heat transfer is? Right? And what we know is what we learned is basically convective heat transfer could happen in two different ways. Heat transfer could happen in two different ways, either in the presence of fluid motion induced by an external equipment, This equipment can be like anything that can pump or compress a fluid, like a compressor, right? Or maybe a pump, or simply a fan. Or the second way of doing this is as a consequence, as a result of temperature gradients and buoyancy effects. And the former is called, the first one, forced convection, as we have learned before. And the latter, the second one, is called free or natural convection. Okay. Please give me a feedback about like whether it's useful for me to write the things instead of just saying verbally, or what do you think?
Yeah, I think it's better if you write it.
Yeah, it might be a good idea for at least like for important arguments. Yeah, it's better if I write it down so that you have a written document. And with the video, it might be difficult to find the correct spot, but generally, if you want to follow the arguments, again, like watching the videos might help. So schematically, we have a system for the forced convection, like a solid at temperature T-wall, okay? And you have, imagine that you have cold fluid, Tf is less than T-wall, okay? And it's blowing in this direction, okay? And the heat is being transferred in this direction, Q, Q. All those Q's might not be necessarily the same. And as we can say, like from experience or like from experiments, either way, experiments are also experiences, right? From experiments, we know that as we increase the fluid velocity, the rate of heat transfer increases, right? So you know it from your daily life, right? If you, for example, have something hot, if you blow air, and if you just, if you blow air, you find that it cools down faster. If you have a hot soup, you know that if you actually blow to the hot soup, it's gonna cool down faster, right? You know these things. And the same thing actually happens for the mass transfer as well. Later we are gonna see. For example, if you have a wet cloth and if you want it to like dry faster, you can put it under wind. and under wind it's going to dry faster because the mass transfer is also faster in a windy air. Okay. So that's our experience. That's what we know. But the question is, what is the mechanism, right? What is the mechanism underlying this effect? It's a very important question, because if we can understand that mechanism, then we can find the relation for the age, right? And we will not need any textbook to give us the information. We can calculate our own age, or maybe we actually have an idea of how the textbook is calculating it, or how the other scientists are calculating and giving us the value of the age, right? So this is an important question in the way to understand how things work, how nature works, right? So another thing from the fluid mechanics, you know, the fluid mechanics course, that I should say, as you forgot what you learned from the fluid mechanics course, that as a result, please never mind me. When I was a student, yeah, I mean, I took this fluid mechanics course, and yeah, I forgot some of the things that I learned in fluid mechanics course. But it's just a matter of, we learn how to actually find the information, and we actually learn where to find the correct information and where to find the correct source. And I'm not blaming you that you're forgetting things. Please don't misunderstand me. And I guess more and more frequently you see these things, you're going to actually get more and more familiar, and the chances are you're not going to forget about them if you use them or see them frequently. And the important things are going to actually appear more and more in chemical engineering. So your brain is going to convince itself that, okay, this is something important, so I should learn. Okay, good. Yeah, so what did you learn in fluid mechanics course? As a result of momentum transfer, within the fluid, in contact with the plate, as in the schematics, okay, a hydrodynamic boundary layer develops. Okay. And the thickness of this boundary layer so let's call it BL, is a function of X, as shown below. Let's show it. So we have the same system. We have this plate at temperature T wall, or maybe let's forget about the temperature for the time being. Let's focus on the momentum transfer. And this air or fluid is flowing, and then this is the initial velocity profile. But then, once it contacts with the solid, at the surface, you're going to have a zero velocity. But then the velocity beyond the surface of the solid is going to get larger and larger, but then it's going to be constant. So if you think about this curve as the velocity and these arrows corresponding to the velocity, and you see that after some point the velocity does not actually change with y-axis. Let's call this y-axis. Okay, and this point where the velocity does not change anymore, right, tells us the interface of the boundary. Okay, where you have this here viscous effect of the fluid is felt, but above this region, viscous effect of the fluid is not felt. Okay, and you can have the same, like a similar profile, but as you go to the left and left in this direction, you will see that the effect of the surface has not penetrated that much into the liquid side. So you're going to have something like this. Okay. Then you have this fluid velocity reached at a smaller y value. Okay. And this is the point where you go from the viscous region to the inviscous region, right? And I'm not going to be able to draw it really nicely, so let me do it this way. Let me redraw this. Let me redraw this. Okay. So that our boundary actually is here. Okay. But at this point, at the starting point, your boundary is here. And if you actually connect these lines, you will see that this thing is the set of points that separates the viscous region from the inviscous region. Okay. Okay, and this thickness is called the boundary layer thickness, and it's a function of x. If you think of this as your x direction, then the red curve corresponds to delta x. Okay, it's a function of x. And just no need to mention, but just for the sake of completeness, this point touching the surface is we have at that point we have the no slip boundary condition. At the surface, meaning that Vx is 0. Okay, and these velocity profiles, they actually approach Vx infinity, and let's call it V infinity. That's also equal to the fluid velocity. You can call it the fluid velocity originally. Okay, and so when the viscous effects coming from the solid is not felt, the fluid is not aware of the effect of the plate, then that means the V infinity is equal to Vf. But more closer to the surface, you feel this effect and it gets closer and closer to 0. Okay, and these lines, you can call them as Vx. Okay, each line has the value of Vx, the velocity along the x direction. Okay, is that clear? And let's summarize. The boundary layer VL is the portion of the fluid in which or along which the fluid velocity changes. Okay, as you can see here, this one, you can see that the fluid velocity is changing, increasing, but beyond that, it's not changing, it's the same. Okay. And delta x is the height at which the fluid velocity approaches the bulk value. Yeah. The fluid, which you can also call it Vx infinity, or simply let's call it V infinity. Okay. We at large y's. Okay. Now, this is like a summary that you're supposed to actually have learned in fluid mechanics course. And we have a similar boundary layer thickness for the heat transfer as well. We have a similar boundary layer thickness. Let's call it delta T this time, T for temperature, for the heat transfer. Okay. So your temperature profile is also gonna not change beyond some point, and that's the value of that point, or the value of that thickness, is called the delta T, which is the boundary layer for the heat transfer. Now, we can have three different situations. We can have three different situations here. So when I ask the question, how does this delta T compare with the delta? So for example, are the viscous effects going, like, penetrating faster than the heat transfer, or slower than the heat transfer? So what are the corresponding thicknesses of the two, delta T versus delta? So you can have either delta T is larger than delta, or delta T is approximately delta, or delta T is less than delta, right? And this, whichever it is, depends on this. Depends, I mean, whichever is valid depends on the properties of the fluid. Okay, and we expect will actually derive later in the course, or at least grow some intuition about this, that delta over delta T, so the ratio of the two boundary layer thicknesses, is proportional or in the same order of magnitude with the nu over alpha. Does anybody remember what the nu was assigned for in the fluid class? We know the alpha, right? The alpha is thermal diffusivity. And as you know, it's K over rho Cp, and as you know, it relates to how fast the temperature effects is diffusing into the deeper into the material. So remember the infinite wall example? We had an actually idea about like the penetration with time, and we knew that like at later times the thing penetrates more and more, and depending on the material property alpha, you can get a faster penetration or a slower penetration, right? And basically that's why when we actually think about the boundary layer thickness of like thermal boundary layer thickness, alpha comes to mind, and you should actually compare it with the momentum diffusivity, also known as kinematic viscosity. Okay, so the how fast the momentum is going to diffuse is just going to depend on the viscosity of the material, the kinematic viscosity of the material. And the kinematic viscosity of the material, as you know, the viscosity normalized by the, not normalized, but divided by the density. Okay, so you basically compare these two quantities, and not very curiously, not very surprisingly, these two have the same units, meters squared per second. They had better do so, right? Because you want to have a unitless quantity here to compare with a unitless quantity. Okay. And there is a name for this quantity, this unitless quantity, because whenever we have a unitless, like non-dimensional number, we like to attribute a name to that. This is called Prandtl number. It's equal to, you can also abbreviate it as PR, and it's equal to mu Cp over K after simplifications. If you divide this by this, you will find that you get this one because the rows cancel, and you get that. That's the definition of the Prandtl number. Now, do you know the reason why we like to give names, why we like to give some importance to the numbers which has no units? Any idea? So whenever we see a non-dimensional number appearing in some form, some expression that has no units, we like to celebrate it and we give it a name. Like when we have an important event happening, we celebrate that each year, right? It's the same thing. We give a name to it and we celebrate it. Why do you think so? So the non-dimensional numbers are very, very, very important. The reason is the following. Imagine you have your like unit system, right? You work with like Fahrenheit. In US, you have Fahrenheit, inches for the length, or maybe feet for the length, pounds for the mass. But in Turkey, we were using kilograms for the mass, centigrade for the temperature, meters for the length. And I actually got crazy when I came to US first, and it was really difficult for me to adapt to new unit system. But anyway, imagine that you solve a problem, you come up with some numbers and so on. Like you say, like this quantity has this number and so on. But these non-dimensional numbers, no matter whether you do this calculation in US or in Turkey, you get exactly the same number. Like it's something like set in stone. It doesn't depend on your unit convention. And if I get, for example, Prandtl number 0.2 in US with US units, I get exactly the same number 0.2 in Turkey. That's something miraculous. And that's why we like to work with non-dimensional numbers, and we because they are universal, and it doesn't depend on your selection of your units. Thus, it actually gives you an idea about how nature works, and it gives you an idea about how materials work, and it gives you an idea about whether a material has a particular property when you compare that number with some other like standard number, a universal number. Okay. And note that here the QW is equal to minus K del T over del Y at Y is equal to 0, right? And this is analogous to what you have seen in fluid mechanics, which is the wall shear stress. Tau W is equal to minus mu del Vx over del Y at Y is equal to 0. Okay. So basically, here we have the wall temperature and wall flux, Q wall, right? But here, what is actually fluxing is basically the tau wall. The momentum is being, momentum is actually fluxing through, right? Do you know the name of this formula, by the way, which is very similar to this thing? That's Newton's Newton's law, right? That's also called Newton's law. One thing which is important is the following. So when we talk about the diffusivity, right, either thermal or momentum, you can actually modify this formula into a form that you get diffusivities instead of the conductivities. So for example, instead of K, you can get the alpha by dividing by rho Cp, right? So basically, you get QW is equal to minus K over rho Cp if you divide by rho Cp and multiply by rho Cp. Okay, so basically this is the energy density, right? Thermal energy density. How the density is actually changing with Y. Here, you can do the same trick. The flux tau wall is equal to minus mu divided by rho and multiply this by rho. And you see definitely that this is also another type of density, and it's called momentum density. Okay. So basically you obtain some like a universal equation like flux of a quantity is equal to minus some diffusivity times the gradient of density of the quantity If that quantity is momentum, this is the momentum diffusivity. If that quantity is thermal energy, this is the thermal diffusivity. Okay, so that's why we call this thing thermal diffusivity. And this thing, momentum diffusivity. Okay, as actually we claimed here. And that's why they have the same units, by the way, because flux of a quantity, gradient of density of the same quantity, they actually cancel it, whatever the quantity is, and you get the same units for the diffusivity. And diffusivity always have the units of meters squared per second, no matter whether it's momentum diffusivity or heat diffusivity, or later we're going to see mass diffusivity has also the same units. Okay. Any questions so far? Okay, so, but look at the analogy between the two. So basically, heat transfer is similar to momentum transfer. And you can say that you can note that the shear stress at the surface is basically what we said as the tau wall, or you can call it tau s. It's minus mu del Ex over del Y at Y is equal to 0. But you should note that the shear stress at any distance is tau, any tau, is equal to minus mu del Vx over del Y, which we're going to use later, okay? And shear stress is restricted to the hydrodynamic boundary layer. Where del Vx over del Y is non-zero. But beyond the hydrodynamic boundary layer, you have it 0 because the profile doesn't change anymore. Like the profile is this changing with Y, and then it's not changing with Y anymore. So this is where you have the del Vx over del Y non-zero, but here you have del Vx over del Y is 0. Okay. And so on. That's the schematics. Now, since we actually have an idea about the analogy between the two, again, analogous to the hydrodynamic boundary layer, in the case of momentum transfer, a thermal boundary layer is formed in the case of heat transfer. in which this time del t over del y is non-zero. Okay, this time there is this flux within the boundary, but there's no more any flux along the y direction beyond the boundary. So schematically it looks like this. Imagine this is T wall. This is a T wall, and you have a temperature profile. Imagine that the fluid is colder. Okay, and you can have a profile like this. This is your y-axis, and this is your t-axis. Schematically t-axis, but it's also your x-axis. Okay, but for this plot, for this plot, it's the temperature that I show with red arrows. And your boundary is here. Okay, because beyond this point you don't have any change in the temperature, but below this point you have a change of temperature. Okay, when the fluid first enters, it doesn't feel the surface of the solid very well, so you just have like something like there's going to be a sharp change. Okay, let's make this here. And it doesn't change beyond this point anymore, and so on. Okay, so this is the interface, and you can actually have something like this, and this is basically delta Tx, the thermal boundary layer. Okay, and this is your t-axis again, and this is your y-axis again, and your fluid is flowing in this direction with a temperature of Tf. So this is the temperature of Tf. Okay, so this is at the temperature of Tw. This is also Tw in the new axis. Okay, any question about this figure? I'm sorry. Okay, so you have a boundary condition here. As you might guess, T is equal to T wall at the surface, the solid surface, right? And that boundary condition is analogous to the no slip boundary condition used in momentum transfer problems. So whatever you have, whatever you have as a temperature in heat transfer, you have velocity in the momentum transfer. So the velocity is fixed for momentum transfer problems. It's 0. But the surface temperature condition T is equal to T wall. T is not 0, but T minus T wall is 0. So you can actually make it look like the same boundary condition as the no slip boundary condition by actually changing the variable. Okay. So so far so good. So we actually introduced the topic. Now next So let's give a break, 10 minutes break, and then we're going to continue with our analysis, and we're going to talk about in more details the boundary layer theory and how we can actually use it to first get an idea about the momentum boundary layer thickness, and then in later classes, maybe not today, but next week, we're going to talk about how to derive the analogy equations between the heat transfer and head heat transfer and the momentum transfer, so that we can get an idea about the value of the H.